Right. So today we will go to the first equation. Law we have it is called the radioactive disintegration law. Right. So first of all, we have to know about the radioactive. What is disintegration? Disintegration is uh, basically the transformation. It is the transformation of the unstable nucleus into a more stable one. So let's say we have sample. Right. So we have a sample. Right. Unstable nucleus. We have here n number of n number of unstable nucleus. Right? Here there are n number of unstable nucleus. 1, 2, 3, 4, n. And after delta p time, after small amount of time, so what would happen? Some elements, some nucleus would be transformed to, let's say, uh, more stable elements, right? More stable elements. So this white represents stable elements. And so initially there was a number of nucleus, unstable nucleus, delta T. After delta T time, some part of, let's say, delta N number of nucleus, at delta N number of nucleus, at delta N number of nucleus has been transformed. Has been transformed. Right. So this phenomena is called basically the disintegration. That transformation from an unstable nucleus to a stable nucleus is called disintegration. And this, so the scientists have found this delta N, this rate of rate of disintegration of a radioactive sample at any given time is directly proportional to the number of radioactive nuclei present at that time. Right? So it is given here. This law states that the rate of disintegration, which means rate of disintegration means uh, number of particles, number of unstable uh, elements transformed into a stable one. That's a number of the rate of disintegration is number of unstable elements, transformed, number of unstable elements is delta n. So delta n number of nucleus has been transformed. Delta T. That is the rate. It's the rate of integration. The rate of integration of radioactive element at given moment is directly proportional to the number of radioactive nucleus. Right? So it is greatly proportional to the number of radioactive nuclei, which is n. Right? So initially n, there were n number of unstable nucleus, and this rate of disintegration is directly proportional to that. Right? So rate of disintegration is directly proportional to that. So proportional to n. N. Then in order to get rid of the proportionality, a constant is implemented, which is lambda. That a constant is lambda. So delta n or delta t. Delta n or delta t. Delta n or delta t is lambda. Delta n over delta t is proportional to lambda n. Lambda is the constant, not proportional, equal. Equal to lambda n. Equal to lambda n. In order to, right? So this lambda is the constant. But here you can see this delta n or delta t. Right? Delta n or delta t actually decreases. Why? Because as this n number, that n number always decreases. That's a number of unstable nucleus. So let's say initially there are we have a sample having 10 number of unstable nucleus. So after some time, what happens out of that 10, maybe two or three would be uh, transformed to stable nucleus. So the remainder would be 7 or 6. Then out of that 6, some around 2 or 3 would be again transformed after some time. And the remainder would be 4. So gradually this n number decreases. So rate also decreases. Rate of integration, rate of disintegration also decreases. So in order to denote this decrease in rate, a negative sign is implemented. Right? Negative side is implemented. So finally we have this. So this is the equation we have. Right? So this is the equation for the disintegration, the law of disintegration. Delta n or delta t is the rate of disintegration. Lambda is called the decay constant. N is the number of unstable nucleus. Right? Number of unstable, not the stable nucleus. Number of unstable nucleus at the moment. At the moment. Number of unstable nucleus at the moment. That's delta n over delta t is the rate of disintegration. Rate of disintegration. Lambda is decay constant. And n is the number of unstable atoms at the moment. At the moment, we are considering number of unstable nucleus at the moment. Right, so this negative sign denotes that rate of disintegration always decreases. That negative sign denotes that rate of disintegration, rate of integration, rate of disintegration decreases. Right, with that. Right, so this is basically uh, the law, the disintegration law. Disintegration law is the for a given unstable sample of unstable nucleus, the rate of disintegration. The rate of disintegration means the number of nucleus being transformed per unit time. That's the rate of disintegration. The rate of disintegration is directly proportional to the number of unstable nucleus present at that moment. Right. So this constant lambda is there called the decay constant. And minus sign implicates that the disintegration rate of disintegration always decreases with that. Right. So now right. So this more basic way. So let's say we have sample having the number of n naught at the start, and n naught is the number of elements at the start. That number of, so we have a sample number of unstable nucleus at the start. Unstable nucleus at the start. So we have n naught number of unstable nucleus at the start. Right? N unstable nucleus at the start. Then, so around t amount of time, the disintegration process happen. Right? So after t amount of time, if n is the number of unstable nucleus, and number of unstable nucleus after t amount of time. After t amount of time, at t amount of time, so we can find this n. And so basically, we have a sample. That's a sample having n naught of unstable nucleus. So after keeping it for t amount of time, so disintegration would happen. Now we have a sample having both stable and unstable elements. So here n denotes the number of unstable elements after t amount of time. So this n can be found, right? So this can be proved using uh, mathematical way, but it is not needed. Just remember n is equal n naught, the initial number of unstable elements n naught, e to the power minus lambda t. At e to the power minus lambda t, where lambda is a decay constant, t is the time. That t is the time starting from n naught. Right. So let's say initially there are 10 unstable atoms, then n naught is 10. right after 10 seconds, starting from here. So you will find an external unstable same. You have 10 for t and lambda decay constant should be given. So it is a constant, it should be given. So this is another equation to find the number of atoms, number of unstable nucleus if the number of unstable nucleus if the initial number of unstable nucleus are n naught and so on. And so here we can see that so we can see that it is so we have e to the power lambda minus t, right? E to the power lambda minus t. So it is the natural logarithm function. So what would be the shape if we plot a graph between the number of atoms, number of unstable elements in and time. So here it would be, so when lambda t is 0, at t is 0, it would be like infinity, right? So this is because of this minus sign, t is at the number denominator. So e to the power 0 is 1, so n naught over, so initially it is n naught. Initially it is n naught. So start from n naught. The graph starts from n naught, and when time goes to infinity, right? So e to the power infinity is infinity. So n naught over infinity. So e to the power this when time goes to infinity, which is a very huge value. So n naught divided by infinity is 0. We have a graph like this. It goes to infinity. Goes to infinity. Right, so this is the graph of n, the number of unstable atoms against time. Right, so you can understand that. So when t is 0, you can put t is 0, then you would have n naught over 1, which is n naught. When t goes to infinity, n naught goes to 0. So we would have a decreasing graph, monotonically decreasing graph. And it is not linear because due to this natural this e to the power term, it is not a linear graph. Right? So then let's say n naught, right? That's the time period. So let's consider the instance where n become n naught over 2. It means this the half of initial number of unstable elements. Right? So let's consider the instance where the n number of present unstable nucleus. Right? N is the number of present unstable nucleus. Number of present unstable nucleus. Right? Number of present unstable nucleus become just half. And the corresponding time period, we call it half time. Right? We denote it by t half time. Right? So half time is just the time required to uh, decrease or required to decrease the present unstable atoms just by half. Right? That's half time. Right? So in order to get from n naught to n naught to half time, that is called half time. So we can find here, considering this uh, region, right? Considering this region, right? So now, after t half of time, remaining number of unstable remaining number of unstable nucleus, which is capital N, is N naught O2, right? Which is N naught O2. Then we can find, so here T is T half and N is N naught O2. So we can substitute these values to this equation. N is equal to N naught over E minus lambda T. Right? So by substituting, so N is N naught over 2, N naught E minus lambda T is T half. Right? So this is T half is just notation. Right? It is just notation. It doesn't mean T into half. It is just T half is just a notation for half time. Then this get cancelled out, and then so what do we have? E to the power lambda T half is equal to 2. Then we can get lambda half by inverse of natural logarithm, which is ln 2. That by taking natural logarithm, we can get lambda into T half is ln 2. So that's another relation between this half-life and the decay constant. Decay constant into half-life is equal to ln 2 for any unstable element. For any radioactive element, half-life into the decay constant is equal to ln 2. This value of ln 2 is so this is a constant. This ln 2 is a constant at around 0.693. Right? So it is a constant. Always the multiplication of the decay constant into the half-life is a constant. Right? Decay constant into half-life is a constant. So which is equal to 0.693 lambda into T half lambda into T half is equal to 0.693 at lambda into T half. At always of decay constant at always the multiplication of decay constant and half-life of a radioactive element is a constant. So other important thing is this half-life. Right? This half-life is also a constant for a uh, given radioactive element. Right? So, for example, we consider uranium, the half-life is constant. We consider some, let's say, carbon-14 isotope, then half-life of that radioactive element is constant. So likewise, uh, depending on the radioactive element, its half-life, the value of half-life is constant. Right? So value of half-life is constant. The value of half-life. So it should be given, either given or we can find it using this above formula. Lambda into E half is equal ln2 if lambda is known. The value of half-life is a constant for a given type of radioactive element. For a given type of radioactive element, this half-life is constant. Right? So now we have two equations actually. First, we learned the law of disintegration. Law of disintegration states that the rate of disintegration is directly proportional to the number of unstable nucleus present at that moment. That number of unstable nucleus present at that moment, dA delta N over delta T is equal minus lambda NT. So minus sign implies that always this rate of disintegration decreases, and lambda is the decay constant. Then we got this uh, expression to find the number of unstable atoms at a given. If the initial number of unstable atoms are naught, right, at naught. So we have n is equal to n naught e to the power minus lambda t. T is the time that we are going to consider, right? That we need to find the number of unstable atoms. Then if the graph is plotted, we have this shape. So here another important consideration is always half time is same. Half time is same, right? It's the time required to change n naught from n naught to which is half is equal to half time. Then what about the time requirement for this to happen? The time requirement to change from N02 to N04, which is again half. The half of N02 is N04. Here, the time requirement for this transformation is also equal to half time. At half time. Then if you consider N08 also, you get the time duration between N04 and N08, which is the half of N04, again would be half-life. Right, so it is very important. This half-life can be found using this expression. Lambda into T half is equal ln2. ln2 is a constant, is 0.693. Right, then so some definition. is called the activity of a radioactive element. Right? It is not actually very different. It is not different from this earlier from disintegration law. Somewhat similar, but there is another definition. So anyway, we have to know about that. So activity is called the rate of decay. Is the rate of decay or the number of decay that occurs within 1 second. Right, the rate of decay. So A. Right, so A is the activity. A is denoted the activity. So it is just another definition, right? So don't get confused. Don't get confused. It is just a definition we have. So it is called the activity of the sample. Of the sample. So which gives, which resembles how active a sample is, right? If the activity, this value activity is higher, that sample is very, is very rapidly decay, right? So rate of decay or rate of disintegration is high of the of that sample. So activity of the sample A is equal to uh, is equal d delta n over delta t. Is equal delta n over delta t. Right, is equal delta n over delta t. Right, so then, so we have, we know delta n over delta t is the rate from the disintegration law. We have delta n over delta t is lambda minus lambda half. Minus lambda half. So from a law of disintegration, from law of disintegration, A can be written as uh, lambda n over lambda t. So lambda delta n over delta t is equal minus lambda n. That's again we get the same expression actually. We get the same expression. Uh, right, so that is just a definition. So activity of the sample is the rate of decay or the number of distribution happens per unit time. So sometimes this so here since, right, so the since is A is proportional to n, the number of, since A is proportional to n, the number of unstable atoms, we can write, we can change. So we have n is equal n naught e lambda minus lambda t. It's equation, right, which we learned here. N is n naught into e to the power minus lambda t. So since they are proportional, since the activity and n is proportional, the number of unstable atoms, so we can interchange. So in the place of n, we can put a. In the place of n naught, we can put a naught e to the power minus lambda t. Right, so we have another expression. Right? So we can change since they are proportional, since the activity and the number of unstable nucleus are proportional. So we can obtain this expression from this previous one. N is equal n naught t to the power minus lambda t. Yeah, A naught is the activity of the sample at the start. Activity of the sample in the beginning or at the start. Initially. At initial. Then this activity, the units for activities, the becquerel, the measurement, the units to find the units of activity is called becquerel, BQ, and another unit is curie, right, CI. Right, so becquerel is the basic unit, and there's another unit to measure the activity which is called curie. And the relation between curie and becquerel is 1 curie is equal to 3.7 10 to the power 10 becquerel. At 10 to the power 10 becquerel. And here some half-life argument. So boron half-life is 0.02. This you don't have to remember. So some half-lives are given. Normally it would be given, right? But to have remember here is laws, that is expression. So first you have to remember this integration law. Delta n over delta t is equal minus lambda into n. And n is equal n naught e to the power minus lambda t. And finally, lambda into t half is equal 0.693 all ln 2. So that's that. Then this expression a is equal to a naught into e to the power minus lambda t comes from n is equal n naught e to the power lambda minus lambda t, because a is proportional to n. Right? Therefore, we can just obtain this a is equal to a naught e to the power minus lambda t expression from n is equal to n naught e to the power minus lambda t. Right? And this half-life is the time period required to decrease the number of unstable atoms to its half value. Right? So, and that is equal. And so time period required to change from n naught to n naught to is, and from n naught to n naught over again half, they are equal. Half-life is always equal, and half-life only depends on the type of the radioactive element. Right? For boron, it is 0.02 seconds. Right? For carbon 14 at 40, it is 5,730 years. For radium, it is 1,602 years. So likewise, the half-life depends on the type of material, only the type of material. Right? You may take this down. In meantime, if you have any question, you can ask. So do you understand? Maybe so we start from here. Radio disintegration law. This minus sign implies always the rate of
So what does the
disintegration.
E stand for?
Sorry?
The E, what does it stand for?
E. Haven't you learned that in mathematics? E? In mathematics, haven't you learned about
It's integration. Integration. In integration, we We haven't learned about it, but it's there.
It is a constant. Is
Yeah.
It's called natural function. E.
In maths,
Uh,
there's another one. E is for coefficient of restitution.
there's another one. E is called the natural function. It has a value of 2 point, the natural function. 2 point, yes, 2.71. This value of is E. Value of E is 2.71. So it is actually a constant which is highly used in mathematics. This E, right? E. 2.7 value is around 2.7, not the exact value. Around 2.71. Haven't you learned about natural logarithm? L. Natural logarithm, don't you know?
This is that E. Yes, okay, I
Yes,
know.
this is that T. The inverse of natural logarithm is equally. So that's how I derived it here. This is that T. Yes, the corresponding natural logarithm. Right. So you may take this down. So here, what would be the units of decay constant? Decay constant, the units of decay constant would be S minus 1.
So in the second one, the integration equation, uh, delta n is n or something else. No.
Are you, so which equation are you referring to? This one?
Yes, now there are two equations, no, that one and the one below. So in the one below, n, is it the delta n above? No, it's different.
N, what is n? N is the number of unstable nucleus. N is the number of unstable nucleus. It is not delta n. Delta n is the number of nucleus which has been transformed to stable ones. Delta n. So here initially there are, so when we consider this sample, so there are n number of unstable nucleus. Right? So that is n. Initially there are n number of, so for example, let's say we have a sample having 10 number of unstable nucleus. So here there are n is equal to 10. Then delta n is the, so what happens, so if there's a radioactive sample and we keep that sample for a specific period of time, what would happen? Definitely some amount of, some number of atoms would be, some number of nucleus would be transformed. They would emit radioactive elements and be transformed to a more stable one. Right? So this delta n is the number of transformation happen during the time period delta t. Right? So if there is a sample having 10 number of 10 initially there are 10 number of unstable nucleus, and after let's say 2 seconds this becomes, now there are only 6. That is transformed to 6. Now there are only 6 unstable atoms. So which means delta n is 4. Delta n is 10 minus 6. 10 minus 6, which is 4 delta n. Right? So delta n is the number of transformation happens. So number of nucleus which has been transformed to stable one during the time period. So delta n and n are not equal. N is the number of unstable nucleus present at the moment. At the moment, the number of unstable nucleus at the moment. Yeah, number of unstable nucleus at the moment. So that is the number of unstable moment present at the moment that we are considering. Right? And delta n is the uh, number of nucleus which has been transferred out of that n, delta n. So they are not equal. Yeah, the second equation n what is the number of unstable nucleus at this? That is constant. Usually, what is the number of uh, unstable element present? Is it no? So do you understand?
Yes.
Okay.
You can scroll below the graph. So we just scroll it down a little bit.
If you finish, let me know.
So now there's a part in the activity place by differentiating the previous mentioned equation. Uh,
I did not include you can try it by your so you have yes, so you have n. You can try that one because since differentiation is not known by everybody, I have not included it here. How the differentiation comes. So by differentiating, you can differentiate this expression n is equal n naught e to the minus lambda t, and you will obtain n is equal so we have n is equal n naught e minus lambda t. So by differentiate it by with respect to t, dn over dt is equal n naught minus lambda minus lambda e to the power minus lambda t. Right, so then we have minus lambda n naught e to the power minus lambda t is equal this n naught over e to the power minus lambda t is equal n. So minus lambda at dn over dt. So therefore we can write dn over dt is minus lambda n. So I just without this proof, I just wrote it. I just wrote the final result here. So this is how it comes. This is the differentiation is not known. I didn't include it here. So you can write this part. Right, so this is n. So again we have minus lambda n.
so we just scroll down a little.
So here always half-life is a constant for a given radioactive element. For uranium, it is a constant. For another one, it's a boron, it is constant. Half-life only depends on the type of the material, type of the radioactive element.
Okay.
So next, yes. So have you ever heard of? Actually, you might have heard of in news, maybe in the news. So archaeologists find very old bones of animals or maybe ancestors, and they say uh, so they were around 5,000 years ago, or maybe 10,000. So how do they do that? Right. So they found and bone here now, and they approximate the age of that. Right. So it is done by it is related to this radioactivity. It is called carbon dating. So that is a method. Carbon dating. So normally the age of those bones are being calculated, approximated using carbon dating. Right? Carbon dating. So if we consider any living being, right? Inside any living being, there consists two types of carbons. Two types of carbon. The mostly common one is carbon 612, carbon 12 isotope. That carbon 12 isotope, and in addition to that, carbon 14 isotopes is also there. At carbon 14, so this should be 14. Carbon 14 isotope is also there, right? Normally, most of these two isotopes are uh, there in any living being, right? Carbon 12 isotope and carbon 14 isotope. And this carbon 14 isotope are this carbon 14 isotope is a radioactive element. Right? So this is a radioactive isotope which would decay over time. Right? Which would decay over time. Uh, this formation of carbon 14 isotope. So carbon 12 isotope is stable, no problem. It won't decay. It is a stable one. This is a stable one. So this is radioactive one. Radioactive. So it will decay over time. So here, this is the way carbon 14 isotopes are being formed. So nitrogen atoms is right struck by a neutron, then forming carbon 14 isotope plus a proton. That's how carbon 14 isotopes have been formed in atmosphere. Right? Basically, they are formed in atmosphere. Uh, and then carbon 14 isotopes, formed carbon 14 isotopes combine with oxygen and form carbon dioxide. Then we know carbon dioxide are they are in a food chain. Right? Chain. Then we eat. Right? So any human being, living being, uh, by food, this carbon 14 isotopes. Right? By eating food, this carbon 14 isotope again. Right? This carbon So we get this carbon-14 isotopes through food, right? Carbon-14 isotopes. Right. So during our lifetime, this ratio, right? So now we have carbon-12 isotope in our body and as well as carbon-14 isotopes. And carbon-14 isotopes are radioactive one. So they are normally obtained from food. And this ratio between carbon-14 isotope and carbon-12 isotope is constant for any living being, right? So during their lifetime, it is a constant 1.3 into 10 to the power minus 12. So you can see this carbon-12 isotope is considerably higher. The number of carbon-12 isotope is considerably higher. This ratio is constant throughout the lifespan of some animal, right? But what happens is after death, so after the death, this carbon-14 isotope would decay. That carbon-12 isotope is a stable one, so it would remain there, but carbon-14 isotope would decay over time. But since after the death, since no food, right, no food is eaten, so what happens? Just uh, with time, carbon-14 isotope would go down. Right? This ratio would change after the death. Right? Before death, this ratio would remain same. So after the death, this carbon-14 isotope would decay, would go down. Carbon-12 isotope would remain same. Right? So this after this, carbon-14 isotope would decay. Right? So when a fossil, a very old bone of a animal or a animal is found, so what can be done here is we can measure right, so we can measure the activity, right? There are instruments to measure the activity, the rate of decay, rate of disintegration of the fossil we found. So let's say we find a fossil somewhere in a cave. So we can there are instruments to measure the activity. And there are instruments to measure the activity of that bone. Right? Later we will look one of that one. Look at such an instrument to find the activity. Right? So A is equal A naught. So we have this expression. Then e to the power lambda t is equal A naught over A. So lambda t is equal ln A naught over A, taking the natural logarithm, then t is equal 1 over lambda, which is the decay constant, ln A naught over A. Right? So A can be found. A can be A is the activity of the current at the activity at the present. Activity the fossil at the moment, at the present time. So when we find the fossil, the activity A is the A represent the activity of now, activity of the fossil at present. At present, whereas A naught is the activity of the fossil when that animal was when the animal was actually before the death of the animal. Activity of the animal corresponding to possible corresponding to fossil before the death. Before the death. Before the death, A can be easily found. A can be easily found. Because using the instrument, we can just measure the activity now. Present activity can be found, but the activity of animal before the death. Right? So it has to be found. Then if we know that, we know A naught and A and lambda. We know lambda, decay constant. We know right. So decay constant of carbon is known. Then we can find the time or the age of the animal. So how long has that animal been there? Right? The age of the animal can be found. So by substituting lambda and A naught and A, T can be found. So that's the method of carbon dating. So A can be easily found, but A naught, to find A naught, so we have this method. So we have lambda over lambda into T half. So this expression actually, from this expression, so we are using this lambda into the half-life is equal ln2. Lambda into half-life is equal ln2 here. Then from that, here lambda can be found. Right? So T half, the half-life of carbon is carbon 14. Half-life is 5,730 years. So you can see it here in the table. Half-life of carbon 14 is 5,730 years. Then by substituting the value of 5,730 years to the above equation, the multiplication of half-life into the decay constant is equal ln2. ln2, the decay constant can be found from there, that expression. Right, so decay constant can be found. The decay constant can be found. Right? Here we have 4 into 10 to the power minus 12 per second is a decay constant. The decay constant can be initially found of carbon 40. Then we know number of carbon 14 nuclei in 1 gram is number of carbon 14. Carbon 14. Right, so in 12 gram, right, so molar mass of carbon is 12 gram. Molar mass of carbon is 12 gram. In 12 gram of carbon, we know there are 6.023 in 10 to the power 23 number of atoms. In 1 mole of any, by chemistry knowledge, in 1 mole of any element, there consists of 6.023 10 to the power 23 number of atoms. This is the Avogadro number. Then in 1 gram, that's a 12 gram, we have 6.0.32 6.023. Then into get 1 gram, we have divided that by 12. So that's why it is divided by 12. Avogadro number divided by 12. Then multiply by 1.3 in 10 to the power minus 12. What is that? 1.3 in 10 to the power minus 12. It is this ratio. Right? It is this ratio. Right? 1.3 10 to the power minus 12. Right? So we multiply 1.3 10 to the power minus 12 by carbon 12 isotope to get the carbon 14 isotope. So here we can get the number of carbon 14 isotope in 1 gram of live sample. And the activity of 1 gram of carbon live sample is we have N. Right, so we have N. So N is the number of carbon 14 isotope, which is this one. Right, so this one into the decay constant, which we found earlier. Decay constant is 0.26. At A naught is 0.26 becquerel. Right now we have A naught, A and lambda. Right? We have A naught, A and lambda, and we can find time. We can find the age of the bone or the animal. And that's called carbon dating. That's called carbon dating
So, sir, how will they ask questions regarding this?
regarding this. So
How?
we'll see a couple of questions. So they might give you the half-life, and yes, they might give you the half-life and try ask you to find the age of a fossil. That is possible. Something like that. Not very hard questions. You will get some simple questions. Actually, this section is very uh, somewhat simpler than the other sections. Uh,
So that 0.698 lambda.
yes,
So for carbon 14 nucleus, multiplication of lambda into T half is 0.698.
9
8
ln2.
or 3?
ln2 is 0.693.
Because
I,
previously we put 6.3, yeah.
0.693. It is the correct value, but here it is given 0.698, right? That doesn't matter. We get the same answer.
Also should be 6.3, right?
6.3.
693, no?
Yes, 0.693. That is the correct one of ln2. So you can change it here. And so that is called the carbon dating. So do you understand how it goes? Then to measure the radiation, so initially there was a unit called becquerel that is to measure the activity, the number of decay per unit time activity. Uh, you may take this down, take this part. Right. So now to for the measurement of radiation, we have another unit called gray. Right. So this unit you have to remember in MCQs they might be asked. So what is the unit of measuring activity? Then you should know it is C. It is becquerel. Then what is the unit of to what is the unit for the radiation? Gray. So the radiation, that means the amount of radiation absorbed by 1 kilogram is called the is equal to 1 gray. The amount of radiant energy or dose absorbed by some matter. Right. So 1 gray is equivalent to the amount of energy 1 gray is equal to the energy, 1 joule of energy absorbed by 1 kilogram of matter. And there is another unit called sievert. Sievert, SV. Sievert, it resembles, so gray resembles the total amount of absorbed energy. Gray resembles the total amount of absorbed energy. Sievert resembles the or harmfulness, right? Or how much dangerous that radiation, the absorbed radiation becomes, right? So harm. So that is that the radiation was rated to produce biological harm or influence the living being. So that is measured by sieverts. So sievert is effective radiation dose, the harmfulness, right? So that is equal absorbed absorbed dose of radiation into Q factor. And so Q factor should be given. So depending on the type of radiation, the Q factor varies. And, for beta, gamma, and X, it is 1. For N, it is 5 to 20. For alpha, it is 20. So you can see alpha rays are very harmful. Alpha particles are very harmful than others. So effective radiation dose. Effective radiation dose. It is the sieverts. Right? It is sieverts. This is the this is the units of this one is sievert, SV. Absorbed dose radiation is gray. GY. Right? So gray into the Q factor gives us sieverts. Right? Gray into Q factor is sievert. So Q factor is unitless. That depends on the type of radiation. And you don't have to remember these values as well. But the equation you have to remember. The effective radiation dose. Effective radiation dose means the harmfulness. Right? The harm. So although 10 joule, let's say the 10 joule of radiation is absorbed by any matter, not all the 10 joule would be harmful to the harmful, right? Let's say only 1/4 of that is harmful. That is Q factor. That is called the effective radiation dose. Is equal Q factor into the total absorbed dose of radiation. That's what did you take this term? This part.
Yes.
Yes. Let's see what's in gray. This units. So gray is the amount of radiation absorbed by a matter. Whereas sievert is the effective radiation, or the amount which contributes to do some damage. That is equal to total absorbed dose of radiation into Q factor. Then these are background radiation, the ways. So you can just go through this, some theories, how the radiation enters to our body mainly. That's so these are from devices such as X-ray machines by consumption of food, gamma rays, and radiation hazards. So always radioactive element should be kept close, right? That's why nuclear plants are they should be protected and very well maintained unless if there was very small leakage or as well, it would be distributed across a very vast region. Actually, you have heard that Chernobyl incident, so it happened in Russia, right? It happened in Russia, but it was found that incident was found in Germany, right? So the German people identified some radiation count, some abnormal amount of radiation count. So that is then they identify that identify that some radioactive leakage has happened nearby. But it happened very in Russia, but it was found there in Germany. So you can so you get the idea that so very harmful because initially it cannot be identified very easily. Uh, so radioactive hazards. Mm, and this is a radioactive detector. Right, so this is a radioactive detector called Geiger-Müller tube. At Geiger-Müller tube. So this is an instrument which can be used to uh, find these radioactive elements. So here there is a cylindrical shaped tube, and this is thin mica film through which uh, radioactive elements could surpass. And this is a anode, which is connected to very high potential, around 500 volt. And this outer surface of the cylinder is the cathode, which is earth through around 470 kilo ohm resistor. Right, and inside the so this is the anode and surface of the cylinder is the cathode. So inside the tube is filled with some uh, gas, like argon, maybe neon, some uh, type of gas. It's normal neutral, argon gas. So what happens here is here when so we have to get this Geiger-Müller tube closer to the place where the radioactivity should be found, right? Where the radioactivity to the place where we want to check whether the radioactivity is present or not. Right. So when we place this Geiger-Müller tube closer to that region, so if a radioactive element passes through this tube, right? If a radioactive element passes through this tube like alpha, beta, or gamma ray, this ionization would happen. Right? So this uh, radioactive elements, right, carries energy. Right? They possess energy, so they could ionize other uh, gas particles. Right? So they could ionize other gas particle. Ionize means the electrons can be emitted, not ionize those other particles. So when a radioactive element passes through this tube, this ionization process happens, right? This big gas ionization process happens, and the positive ion would be attracted towards the uh, cathode, whereas negative ion would be attracted towards the anode, right? Negative ion would be attracted towards the anode, and positive ion would be attracted towards the cathode. So due to this high potential difference, then that ion would attracted uh, charge would flow through the would flow through the flow through this wire to the earth. Then we know uh, from delta equal IR and delta equal IR. So charge flowing through a conductor is the current, right? A charge flow through a conductor is a current. from delta equal IR. So we have I, we have R. Here this is R. Then by measuring the voltage across this resistor, right? So when the current passes through this conductor, a small spike would occur. Right? So when a voltage is measured using a, let's say, some oscilloscope, oscilloscope now, which we learned in current electricity, right? So you can apply an oscilloscope across this resistor, and when current flow through this, right? So when current flow through this, or when a charge flow through this, small spike would be there. Right? So that's how we can find the radioactivity. Right? Then there could be a we can attach a small alarm, so that beep sound would be there. So if there are more radioactive elements, this high amount of spikes would happen. Like if there are very less number of radioactive elements, this spike would be happen rarely from time to time. And we might get beeps with small amount of beep with higher interval. But if there are a higher number of radioactive elements, there would be a higher number of spikes closer together. So we might we hear the beep sound very rapidly. And so that's the method. This Geiger Muller tube, right, which can be used to identify the radioactive elements. Mm. Now let's go for some questions. Let's try the 10th question. 10th question. 10th question. It does if the mass of a radioactive sample is doubled. The mass of radioactive sample is double. Which of the following is correct regarding its activity and its half-life? Mass of radioactive sample is double. Which of the following is correct regarding its activity and half-life? So can you tell me the answer? Try to find the answer.
So does the mass depend on anything? Does anything change?
Yeah, that's the case here. So half-life doesn't change. Exactly, half-life doesn't change. But activity, because half-life directly depends on the type of the material. Like if it is carbon, maybe it is 1 kilogram more, 1 gram more, 1,000 gram, 1,000 kilogram, doesn't matter. Half-life remains same. For carbon, half-life is 0.02, as I remember, 0.02. So half-life doesn't change on the mass, but the activity, activity, does activity depends on mass?
Yes, it does.
Yes, it does. Right?
Yes.
Activity depends on mass because activity is
The
equal.
rate of decay now.
Yes, activity is
Decay per second. So, I mean, if they increase the mass, the rate of decay also has to increase.
yes. So if mass is increased, this n would increase. right? N would increase. N is the number of unstable elements, right? Number of unstable nucleus. Number of unstable nucleus. So if we get, let's say, M, M sample of having mass of M. So let's say we have 5 number of unstable nucleus. So if you get 2M of the same sample, twice of mass, there would 10. Right? Approximately there would be higher than 5, right? Higher than 5, maybe 10 unstable elements. So N is increased. So here N is 5, here N is 10. So when N changes, A changes, activity changes. When the number of unstable elements in the sample changes, activity changes. So A changes, A increases, but half-life remains same. Remains same. Third one, activity increases, half-life remains the same. Half-life is not affected by N. Half-life is a constant for any given type of radioactive element. It is a constant. For uranium, it is constant. For carbon-14, it is 5,730 years. Right, so that's then 11 is very easy actually, right? What is the answer for the 11? 11. Dimension of
So T.
dimension of lambda T or T minus 1. It will be T minus 1, right? So you know S minus 1 is the units of that, then T minus 1. Or I'll say you don't know. We don't know anything. So always index. The dimension of the index should be what? That's the dimension of the index. Here index is lambda T. Should be 1. So dimension of lambda into dimension of T is 1. Dimension of y is T minus 1. That is T. Then dimension of y is T minus 1. Right? Uh, that's the second one. Then let's try the eighth one. Eighth question. In eighth question, it is a fossil is found to be 72,000 years old. Found to be 72,000 years old by carbon-14 dating. That we discussed earlier. If the half-life of carbon-14 is 6,000 years, the ratio of carbon-14 present in the fossil, the amount of carbon-14 present in the living tissue is half-life is given 6,000. So this is 72,000 years old. A ratio between amount of 14 present in the fossil and amount of 14 carbon present in living tissue. So if initial number is n naught, then after half-life t half, it would be n naught or 2. Right? Then again after another half-life, it would be n naught over 4, right? N naught over 4, which is equal n naught over 2 to the power 2. Then again another half-life, it would be n naught over 8, which is n naught over 2 to the power 3. So here this value is index of the 2. Index of 2 is equal to the number of half-life. Right? So here index of 2 is equal to number of half-life. So we can have n, the number of present unstable elements, is equal to n naught over 2n, 2n, where n is the number of half-life. Number of half-life. Number of half-life. So n is the currently present number of atoms, unstable atoms. N naught is the initial. Initial number of unstable atom. So here in this case, right, so in this case, number of n is equal, number of half-life is equal 72,000 divided by 6,000, which is 12. 12. And n is 12, then we get n is equal n naught 2 into the power 12. So n naught of n, so they're asking about n over n naught is equal 1 over 2 to the power 12. That's the amount of 14 carbon present in the fossil divided by amount of 14 carbon present in the living tissue, which is the initial number of carbon in naught. So 1 over 2 to the 12, 2 to the power 12, fourth one. And so number of unstable atoms is equal to the initial number of unstable atoms divided by 2 to the power n, where n is the number of half-lives. Try 14th one. In 14th question, an archaeologist extracted 100 milligram of carbon from an ancient wooden tool and round it is and found it is 1/4 as radioactive as 100 milligram of carbon extracted from a light tree. Half-life of carbon is 5,730. How old is the wooden tool? How old is the wooden tool? So 1/4 of radioactive. Right. So radioactivity has been decreased by fourth, 1/4. Right. So they are given this one, NO N naught is equal 1/4. Right. NO N naught is 1/4. Which we know that 2 into power n. So yeah, n is 2, right? So in order to have 4, n should be 2. N means the number of half-lives. Number of half-lives. Number of half-lives. Number of half-lives, so the age. hence the H. H is 2 times of 5,730. 11,460. Yes. Fourth one. Then 26 question. So 22, 22nd. 22nd, say a radioactive material has a half-life of 60 minutes. Half-life of 60 minutes, the percentage of fraction of the material that has decayed in a period of 3 hours. At 3 hours is 3 times of half-lives here. In this case, with 3 times of half-lives. The percentage of fraction of material that has decayed during a period of 3 hours. So how many half-lives are there? Are 3. And 3 half-lives are been surpassed. Then N naught. N naught is 1 into 2 into the power 3 is 8. Is 8. So N is N naught of 8. So there are N naught of 8 currently present. Right? Currently present number of unstable atoms is N naught of 8. Then the decayed amount of decay. So this is the currently present unstable nuclei. Currently present. Unstable nuclear. So amount is been transformed, which is been transformed. Amount which has been transformed. Amount which has been transformed is N naught minus N dash. N dash is N naught minus N naught of 8. Right? Now current initially there were N naught amount. Now it is there only N naught of 8. So the amount which has been transformed is N naught minus N naught of 8, which is 7 N naught of 8. So they are asking about the percentage of fraction of material that has been decayed. Fractional percentage fraction which has been decayed. Percentage fraction which has been decayed. 7 n naught over 8 n naught into 100%. At 12.5 into 7. $87.5. 87.5%. We have get the difference between. So from this expression, we would get the currently present unstable atom. So to get the amount which has been transformed, we have to get the difference between the initial number and currently present. So which is 7 naught n naught of 8. Fifth thought. Is the answer. So here there are some additional questions as well. So I will attach this to the answer, so you may try them. Uh, yes, so I will attach them. So today we actually conclude the radioactivity part as well. Right, so these expressions, the disintegration law, and the relation between half-life and decay constant, the activity of a radioactive element, and carbon dating, those things, and Geiger-Müller tube is used to detect the radioactive elements. So next we have some theories actually. Only theories related to what is nuclear fusion. We will look what is nuclear fusion and fission. Uh, finally, finally, the subatomic particles. That the particle physics section, which is mostly theory based. No any equations. Most theory based. Simple. Simple theories, right?